Friends, let us continue from where we left earlier yesterday. So, we were discussing, let me remind you what we were discussing. So, we were discussing the applications of Gauss law, and yesterday we have seen the electric field intensity due to the uniform charge non-conducting sphere and line of charge, infinite line of charge, and also we have seen the electric field due to it's a cylindrical body, right? It's a metal cylinder or uniformly charged long cylindrical conducting surface. And we have also seen electric field intensity due to the non-metallic, that means non-conducting cylinder. Let me repeat few points, few derivations of yesterday, and then we move further. Okay, let us see the yesterday's derivation little bit. I would like to repeat within few minutes. So, this is what is due to long charge cylinder, and let us suppose conducting, both let us see conducting and non-conducting. I just finish not explaining in detail, but just I will finish the derivation for the just recap sake. So, a conducting cylinder is a one which is whose charge is always lies on the surface. So, this is the axis of the cylinder, this is the axis of the cylinder, and sometimes you can also say this is metal cylinder. Metal means that is conducting, right? As we know, this is actually long cylinder. I have taken a few portion of that, a little portion of that. Now, there is a point here imagined outside, and the point can be imagined on, point can be imagined inside. Then we constructed a Gaussian surface. So, the charge always resides what on the surface now? Charge resides on the surface, curved surface actually. So, on the surface, therefore, we define surface charge density. This is what we did yesterday, right? Surface charge density. Surface charge density means charge per unit area, that is sigma. We construct a Gaussian surface. What sort of Gaussian surface let us imagine? We construct a cylindrical Gaussian surface. We construct a cylindrical Gaussian surface, right, like this. And I told the rules in constructing the Gaussian surface. The Gaussian surface should be always such that the point should lie on the Gaussian surface, first point, and the electric field due to the charged body should always parallel or perpendicular to the Gaussian surface. That is a rule, right? It's not the law, but convenient rule. Okay. And the electric field lines are away from this like this. So, there are three surfaces here. This is the one surface you can imagine, and the curved surface is the second surface you can imagine, and the another cap here, this is the third surface. The total flux is, the net flux what you can write is E dot ds is equals to 1 by epsilon naught into charge enclosed by the Gaussian surface. Of course, in this case cylindrical surface. Now, what we do is this integration performed in 3 steps: on the first surface, on the second surface, and on the third surface. So, every time we do not take all this, but anyway, for understanding this is very much required. So, E dot ds 1 by epsilon naught into charge enclosed. Now, here for the first surface, the area vector is in the upward direction and the electric vector is like this. So, the angle between E and ds is 90, therefore, this is E ds cos 90, cos 90 means 0, this vanishes. Similarly, the third one, the area vector is in this direction, the E vector is in this direction, again the angle is 90, this also vanishes. Only this is actually not a line, actually this is a curved surface, right, or the lateral surface we say of the cylinder. So, then if you integration of the angle between any area element and electric field element is 0, because they are parallel. Okay. Now, E ds cos 0 is 1, then integration of ds, you will integration of ds, you will get 1 by epsilon naught into charge enclosed. What you can write? The charge inside the Gaussian sphere, Gaussian cylindrical surface is nothing but the charge on the actual cylindrical body, right, that is distributed on its surface area. So, what you can write is sigma into the surface area of that is nothing but 2 pi r l, that is the surface area of the cylindrical charged body, right, 2 pi r l, and l is the length of this Gaussian cylindrical surface. Now integration of ds, what you will get, that means this is, you can write the distance of the point, we always consider r, so E into 2 pi RL. This is also surface area of the Gaussian cylindrical surface, lateral surface area, and you can finish now like this, sigma into 2 pi RL, 2 pi or 2 pi L cancel here, you will end up with like this. So this R is here, sigma is there, R by epsilon naught R. So this is the final answer. From this, E outside point is, this is outside point we are considering, 1 by R. And on the surface, second one, on the surface, what changes will occur is, this small r becomes equal to, this small r becomes equal to capital R, then E on, what you will get is sigma R by epsilon naught R, R also cancel, so E on, what you will get, sigma by epsilon naught. And we are very much clear with the information that in the metal cylinder, inside there won't be any charge. Therefore, the flux, if you imagine any Gaussian cylindrical surface inside, no charge is enclosed there, therefore the flux is 0, therefore E inside is simply 0. So this is what we got yesterday of the metal cylinder, and I will repeat that electric field due to. So when I keep these two derivations side by side, there won't be any confusion here. Long charge cylinder, non-conducting cylinder. This is the important difference between these two. So whenever I say non-conducting cylinder, immediately you have to understand the charge is uniformly distributed. The charge is uniformly distributed throughout its volume. Distributed throughout its volume. So immediately what parameter you define is, we define charge density, the volume charge density rho, that means charge by volume. So this is the difference. Previously we defined sigma. Why sigma here? Because the charge is residing on the surface. Now the charge is spread throughout the volume. Now let us come to the basic diagram here. So this is the long cylinder. Throughout the body, the charge is spread. Let us suppose the charge is Q anyway, right? In order to calculate the electric intensity outside, let me redraw the picture here. So this is the non-conducting cylinder, where charge is completely spread all over its volume, the body, and this is the axis of the cylinder. The radius of this is R. Now the point is here. We imagine again Gaussian cylindrical surface like this. Same thing, but the difference is there is charge overall. This is the Gaussian cylindrical surface. This is okay. Now, if you apply the point outside, what we do is, this is at a distance r, the length of the Gaussian cylinder is L as usual. This is area 1, this is area 2, this is area 3, 1 and 3. Again same story, means intensity, no flux is through 1 and 2, 1 and 3, only the flux is passing through second surface. I am writing directly E dot ds through the second region, that means the curved region, is equal to 1 by epsilon naught into charge enclosed by the Gaussian cylindrical surface. So E ds cos 0, then E can take out integration of ds 1 by epsilon naught. How we can write the charge enclosed? Whatever the charge is on the cylindrical body, in this one, that is the charge enclosed there. You can write the charge density, means charge per volume, into volume of the inner cylinder, wherever the charge is residing, right? That is given by pi r square L. So ds is what? Ds is nothing but the surface area of this, that is 2 pi r L. Pi cancel, you can cancel L also. So what you will get is E equals to rho r square by, this is 2 epsilon naught r. So this will be the answer for the outside point. So again you will understand E proportional to what? 1 by r, just like this. Now on means easy. Second point is on the surface. On the surface, that means r equal to r, you will get simply rho r square by 2 epsilon naught r rho r by 2 epsilon naught. This will be the value of the intensity on the surface. Now the third point is inside. The point inside, let us elaborate this one. Yesterday this was not telecasted, I think. So let us be more clear on this point. So this is the original cylinder. Let me show little bit exaggeratively. And this is a long cylinder. Okay. Now the point is inside. So we construct a Gaussian cylindrical body around the point P. The point P is at a distance r from the axis again. So for the same region, this is area 1, this is area 3, this is the curved area 2. That story is same. The flux is only through a lateral surface area. Don't get into that. Therefore, E dot ds will be integration done only on the curved surface is equal to 1 by epsilon naught into charge enclosed. Charge enclosed. So E dot ds means, let me write directly, E into, what is integration of ds? Integration of ds means 2 pi rl, that's L is the length of the Gaussian cylindrical surface, is equal to 1 by epsilon naught charge density, charge enclosed. What is charge enclosed? Charge density into the volume of the inner one, that is pi r square L. This is where the charge is enclosed. So the volume of this should be taken, not the volume of the outer region. So immediately what you can cancel is pi you can cancel, r, one of the r you can cancel, L you can cancel, E is equals to rho r by, you will get 2 epsilon naught. So this will be the at inside point. Now as a standard results, you remember all of them. On inside you can see clearly inside proportional to r. If you plot a graph for this, so how you remember is proportional inside r, that means it's like this. Then after it will be inversely proportional to 1 by r, as we have seen here. So this is the graph, looks very similar to the what? The spherical non-conductor, but only the difference is here it will be r square, 1 by r square, that's the only difference. So this is E versus R graph for the showing the non-conducting cylinder. Now if you compare these two, then you will understand, you don't make any mistake. Compare, keep them side by side derivations and understand them, and then you have to remember the formulas of the standard results. You must remember the final results. That's important here in the entrance point of view. Let us get into the next topic here. Now let us see E due to uniformly charged large non-conducting sheet. This is very important. What is the nature of the charged body is? It's a uniformly charged long non-conducting sheet. Previously also we derived this one based on the basic electrostatics principles there. Now we are going to derive the same thing by using what? Gauss law. My advice to you is, you keep the derivation in front of you and then see this derivation and then compare the end results. Then you will understand better way, right? But if you isolatedly study that one and if you isolatedly study this one, there will be a confusion always. So my advice to you is, keep the derivation in front of you and then understand that one, repeat that one once and then look to this derivation, then you will understand in a better manner. Now this is a long uniformly charged sheet. Actually this is a plain sheet, non-conducting sheet, therefore the charge is spread all over like this. This picture, by this you can imagine what is the kind of sheet is this. So immediately you define one thing, that is sigma. That means, what is sigma there? Surface charge density. Surface charge density, right? Charge per unit area of the sheet. This is very long, means it is extended like this, extended in this direction and extended also. A little portion of that is shown here. It is much larger sheet, okay. Now this picture, let me show in this cross section manner. In this cross section, let me show the same thing. So this is the charge sheet of some thickness, very small thickness, and the charge is spread, sorry, not spread on the surface, but charge is like this. Now, because of this charged sheet, let us try to find the intensity at a point P, some distance r. Okay. What we do is, we have to construct a Gaussian surface before we apply the Gauss law. You may be well aware of this. So, actually sheet is like this, the point is here. What kind of surface is suitable here? You have to think over it. The point I told you is the electric intensity should be either parallel or perpendicular to its area of cross sections, right? So, therefore, if you think a little bit further, the immediate answer you can think of is a cylindrical surface, a cylindrical symmetrical Gaussian surface you can imagine around this charged sheet, like this, where the point P is on one of the caps here. This is actually on the board, you cannot see, but imagine that one sheet is like this, the cylinder cap is here, the point P is lying on that. On the other side also symmetrically, there is one more point at distance, same thing, R from the charge sheet. Now, there are three phase surfaces here. This is 1 and this is 2 and this is 3. This is one surface and the curved surface is there, that is nothing but second. What is the direction of electric field? Direction of electric field is like this. So, you can easily imagine if you take the curved surface here, the area vector will be taken on the curvature like this, that is in this direction, and E vector is like this. So, this is 90 degrees. But whereas if you see the caps here, if you imagine area element here, that is in this direction and E is also in the same direction. Similarly, if you imagine a area vector here and the electric field lines are also diverging from this, moving away from the charged sheet. Once you have this picture, the rest is simple. Easily you can finish the derivation. So, what is the Gauss law? The net electric flux is equals to 1 by epsilon into charge enclosed by the surface, the Gaussian surface. Okay. Now, actually this is not a line. Imagine this is not a rod. Always remember the picture is like this into the board. The cap is having some area and here the sheet is also having the same area. So, this point you try to understand. Whatever the cap area I am drawing here, suppose if the area of this one is ES, the same area is projected on the sheet. That means, whatever the charge is there in this surface area is enclosed by this Gaussian cylindrical surface. You have to understand that. So, immediately I can write 1 by epsilon into sigma into what you can say? S, you can say sigma into S. So, this is also, you will get the picture here. Let me draw this one. This is also picture on this, the cap projection here on the sheet. Now, one important thing is, this is E dot ds actually, but there are two things here. The two surfaces upon which the flux is there, the right side is there, left side is there. Therefore, let me say this is 1, you can say 1 E dot ds and plus this I said 3, the 2 anyway 0 because 90 degrees. So, E dot ds is equal to 1 by epsilon into sigma s, right, sigma s. So, E ds cos 0 is 1 anyway, E is taken out, integration of ds means the area s, this area is I have taken s, this also area s, therefore, 1 by epsilon into sigma into s. So, what you can write here is 2 Es is equals to sigma s by epsilon s, cancel here. So, E will be sigma by 2 epsilon naught. So, this is the same results we got earlier, but this is a very simple way of getting the same answer. Remember this standard result and then I will explain E due to uniformly charged long conducting sheet, that is the only difference, right. Now, let me rub the board and come back. The only difference here is, friends, this is due to uniformly long conducting sheet, the only difference is this. So, whenever I mention here the charge resides on the on its surface. That's the important point. Therefore, immediately you define sigma is surface charge density. And let me show the picture, imagination here. It will be like this, right? This is actually the body here. This is one surface. On the other side of the board, also the charge is spread. The charge is spread on its two surfaces. So let me write here clearly. The charge is spread on its two surfaces uniformly. How they are spread? Uniformly. The other side I cannot draw here, but let me imagine like this. The charge is there, background also, right? And let me show the cross section of this. The cross section, let me show. This is the cross section of that, okay? And this is one surface into the board and out of the board. This is not a line. Remember, this is not a line. So the charge surface, actually it's like this. Into the board is there, and into the board is there, out of the board also you can imagine. The surface on which the charge is spread, not inside. So therefore, inside, here inside, in this region there is no charge lying. So again I have shown here also clearly, there is no charge lying within the body, right? That's the difference. Now, if you consider point P as before, that's the goal here. Consider a point P some distance, right? At some distance from the axis, from the sheet here, let us suppose R. And what we do here is, we construct a Gaussian cylindrical surface similar to that. But there is a difference here. We construct only this cylindrical surface. You can also take a symmetrical point on the other side. There is no problem there. But if you consider that, you have to take the two charges there. That means this is sigma, here also sigma, here also sigma is there. Surface charge density on this one is sigma, on this one also sigma is there. If you would have taken here another symmetrical point, the only difference comes is you have to take the two sigmas here. Therefore, the charge within the Gaussian sphere is 2 sigma s you have to take. So that is also okay, possible, but let me, for the simplicity's sake, let me imagine the Gaussian cylindrical surface on one side of it. And now you can clearly take again, there are three surfaces here. This is 1, and this is a curved one, 2, and this one you can say 3. And the flux is, you can say E dot ds, very simple. Now I think you are comfortable with this sort of equations and the Gauss-like explanations, because we have been doing for the last few days. So E dot ds on the various surfaces, let me write on the first surface, let me integrate on the second surface, and let us integrate on the third surface as well. Then what you will get is, you have to think on which surfaces it will vanish and where it survives. Where the integral survives and where it vanishes, you can easily imagine on the one. On the one it survives because ds is like this, E also in the same fashion, direction is same, so angle is 0, cos 0 is 1. And the area of this one, let us suppose S is the surface area. S is the surface of the cap and also surface area of the charged sheet within the Gaussian surface. So you can say this survives. What about second surface here? As we understood earlier, ds is like this, angle is 90, it won't survive because cos 90 is 0. And what about the 3 here? Where it won't survive as well. The reason is, here there is no inside electric field is there. It's not about the angle, it's about the E0, therefore it also vanishes. So in the picture, what remains is only the first surface remains. So therefore, E integral of ds, what you will get is Q enclosed. What you can write is how much charge is enclosed within this charge is enclosed within that. Therefore, I can write sigma S. I can write sigma S. I can write. So integration of ds means that is also I have taken S. So 1 by epsilon sigma S, SS cancel. So E equal to what you will get is sigma by epsilon. See the difference. Now you compare the difference for the non-conducting sheet and conducting sheet. Let me write the two results here. For the non-conducting sheet, so that you don't make any mistake in applying them in numerical problems. For non-conducting sheet, E equal to what? Sigma by 2 epsilon. For conducting sheet, what you will get is E equal to sigma by epsilon. These results are important here. And you can observe one more thing is independent of the distance. Independent of the distance of the point from the charge distribution or the charge sheet. That is naturally you can expect, because this is very large sheet we have taken. Therefore, E is almost uniform near the sheet, that you can easily imagine. Just like the gravitational intensity is uniform on the earth surface, almost uniform, right? So because earth looks like a flat, actually it is not flat. You understand that point. And let us leave this point and move to the some examples here that will help you understanding the flux law, the electric flux and the Gauss law. By some example problems, you will understand them better, and those problems I have chosen which are already asked in the previous examinations. So let us get into that now. Now, students, let us get into some basic problems. You will understand now perfectly the concept. Let me read out the question to you. A charge Q is placed at a distance a by 2 above the center of the surface of the edge. So this is actually a square surface. Edge is given A and the point is taken at a height of a by 2 from the center of this square surface. And the electric flux through the square surface is how much amount of electric flux is passing through this particular one. Where the charge is placed, here. Before getting into this, I will explain the very fundamental concept. Let us see the solution here. Suppose if the cube is there, you imagine a cube like this. Okay, thus edge is of length A like this, and the bottom surface is actually every face of the cube is a square. You know that, right? Every face of the cube is square. How many faces it is having? 6 faces it is having, top and bottom and top, and the 2 side faces, up and the back, right? The upside and background of this. So there are 6 squares you can imagine. Now, where is the charge here? The charge is at a by 2 means this height is also a. A by 2 means exactly at the center. A by 2 means exactly at the center of the cube, you can imagine. Now, the flux through all the faces, what can I say is, because it is a symmetrical situation, the charge at center means completely symmetric. The flux through the entire cube is nothing but net flux is 1 by epsilon into charge enclosed. This is a general formula of the Gauss law. How much charge is enclosed by all the faces? Therefore, you can say Q here. So the flux through the entire cube, is equal to Q by epsilon naught. But if I ask the question to you, what is the flux through one of the surface? What is the flux through one of the surface? Let us suppose this is A, B, C, D, or you can take any surface like E, F, G, H. Flux through one of the surface means how much charge is belonging to one surface. Because there are 6 surfaces, they are all holding the cube. How much one surface hold the charge? Naturally, the charge is equally distributed, equally belongs to all the 6 faces. Therefore, you can imagine 1/6 of the charge belonging to one surface. You have to understand this point clearly. Therefore, let me write that also. Every surface 1/6 of the charge belongs to one surface. Why 1/6? Because there are 6 surfaces are there. Therefore, 1/6 belongs to one surface. Therefore, flux through one of the faces is 1 by epsilon into charge enclosed by that surface is 1/6 of the charge. You can answer q by 6 epsilon naught. Why I am telling all this is, some of you might have understood why I am telling all this, because the question is based on this concept. This question is based on this concept. How? Now see, only one face is given. Now let me come to this question. Let me redraw the diagram here. This is 1 square, edge is something A. But what you can do is, you can construct a cube here around this. You can construct a cube around this. See, now the picture is similar. Where the point is there? It is exactly at A by 2, means at the center. At the center of the cube. Therefore, the flux through this surface, means one of the surface is nothing but already I said. Therefore, the flux through this surface, what is given? The square face is, how much charge belongs to this? 1/6 of the cube belongs to that. Therefore, answer will be q by 6 epsilon naught. Actually, the problem is based on this. If you already know that, you can extrapolate this. You can imagine something of that sort, then you will answer quickly within no time. I hope you understood this. So, the option is second, and let us move into the next question now. Friends, this is one more question I have come up with. It's an easy question, but more fundamental. But many students, if you do not understand the basics, you will be landing in with a wrong answer, right? Now, let me read out the question once. 4 closed surfaces, 1, 2, 3, 4, they are given here, and corresponding charge distributions are also shown. How much charge is there within and out, everything is shown. Let the respective electric fluxes through the surfaces be. Because of this, the flux is phi1. Because of this, the flux is phi2. Because of this, flux is phi3, because the surface is S3, and that is phi4. And the relation between those fluxes is the question. So, this is the straight away the statement of the Gauss law. If you understand, you can answer this one. What Gauss law? Let me get into the solution here. So, what Gauss law says? Gauss's law says the net flux through any closed surface, is equal to 1 by epsilon time into charge enclosed by the surface. Clear? Now, phi1, from the same concept, let us get into phi1. How much is charge enclosed by this surface? 2q. So, this is 1 by epsilon into 2q, or simply you can say 2q by epsilon naught. Let us suppose this is equation 1. What about the second surface? 1 by epsilon time into the charge enclosed is, you can say q plus q minus q. So, one of the q cancel here, then you will get again 2q by epsilon naught. This is equation 2. Now, what about the third one? See, there is one charge, some charge phi q is out of the surface, but Gauss law says charge enclosed by the surface. Therefore, we need not consider this charge. This is out of question, isn't it? So, therefore, phi 3 I can take how much charge enclosed is Q plus Q, that is also 2Q by epsilon. In the similar logical steps, according to the way we analyze this one, in the same reasoning, we can answer this one also. 3Q is not effective, 3Q is not included in the surface, so therefore we do not consider 3Q in the flux calculation. Therefore, what we do is 8Q minus 2Q minus 4Q, and this is also 2Q, so epsilon naught. So therefore, all the fluxes are equal magnitude. Therefore, we can say phi 1 is, phi 2 is, phi 3 is, phi 4, and let us go the options is you can go by the third option here. A very simple question based on the very fundamental concept. Therefore, we must understand each and every point correctly in the right sense, then there won't be any problem in answering the numericals here, right. Let us get into the third question now. Now, let us discuss the third question here. The electric field in a region of space is given by, in the vector notation given, E naught I plus 2 E naught J. That means, along the x direction, the magnitude is E naught, along the y direction, the magnitude is what? 2 E naught. Where E naught value is also given, the magnitude is also given, 100 Newton per Coulomb. The flux of the electric field through a circular surface. The question is this: the flux of the electric field through a circular surface of radius 0.02 meters, and how the circle is there parallel to the yz plane. That is important here. Now, let us imagine this one. Now, this is x axis, and this is y axis, and this is z axis. And the electric field along this is, that is E naught, the magnitude. Along this one is how much? 2 E naught. See here, E naught is along x direction, 2 E naught along the y direction. And this is what actually, this is x axis, this is y axis, and this will be z axis out of the board, and this will be the y, this all plane is yz plane. So because the z is like this, so this plane is yz plane. Therefore, one circular cross section is here. Let me draw here. This is the circular section like this. So clearly, E naught is passing through this one, and the area vector, if you imagine, the area vector is also like this. This is area vector. And what is 2 E naught here? 2 E naught is perpendicular to the area. Let me write that. E naught component is parallel to the area vector, and 2 E naught component is perpendicular to area vector. Therefore, the flux through this circular cross section is completely due to this E naught and not because of this 2 E naught. Therefore, the flux through this area is only because of E naught. I can write the net flux is E naught A. Simply what? Because cos 0 is 1. Cos 0 is 1. Actually, you have to write E naught dot A cos 0. But cos 0 1. So E naught is how much? That is given 100. Area you can write pi r square, 100 into 3.14. The radius is given as 0.02 meters. You can write 2 into 10 to the power of minus 2 meters. Square of that. Now, if you simplify, you will get some answer here, right? So, this 100 10 to the power of minus 4 is 10 to the power of minus 2. Let me simplify 4 for 16, 5, 12.56, 10 to the power of minus 2. Therefore, 0.1256. Come back to this one, 0.125. So, the first option, 0.125 is given. 6 of course you can ignore, Newton meter square per coulomb. So, Newton meter square per coulomb. Therefore, the option you can go by is the first option is correct. Let us get into one more problem now. Take down this. Let us get into next one. Now students, let us get to one more interesting question here. Let me read out the question for the clarity's sake. The flat base of a hemisphere, it's a hemisphere, right? Half the sphere of radius a is given. The radius is something a is given. Now with no charge inside it, no charge is inside it, that is given, lies in a horizontal plane. So this is a horizontal plane on this hemisphere is situated, right? A uniform electric field is applied at an angle of 45 degrees pi by 4 with the vertical direction. The electric flux through the curved surface is, so hemisphere is having a curved surface and the flat base, you try to understand. The options are given and the diagram is also provided. Let me read out the diagram and explain something deep here. Not only this question, I will answer one more question here related to this. Suppose you imagine a hemisphere like this. So the base is like this, the radius is, the base radius is a. Now let us take one more case here. The electric field is like this. So this is piercing the base and coming out of the curved surface. Let us suppose it's like this. The flux is coming and going out of the hemisphere. What is the net flux here? Net flux is 0 because whatever the flux is coming in is going out as well. So the net flux is 0. So I can say the net flux is 0. That means whatever the flux is coming in through the circular base is also equal to flux out through the curved surface of the hemisphere. If you understand this point, that will be so simple. So whatever the flux coming through the circular base, easy to calculate compared to the flux going through the curved surface, because in a curved surface everywhere the angle is different, okay? But in a circular base, if you imagine any unit area here, the angle between E and DS is 0. I am talking about the circular base, I am not talking about the hemisphere, right? Therefore I can calculate here, this is nothing but E dot A, EA cos 0, the area of the circular base, area of the circular base. So E into what is circular base? Pi A square is nothing but flux out through the curved surface. Therefore the question is the flux out through the curved surface, the answer is into pi A square. This is the previous knowledge you should have in order before answer this question. The only difference here is in this question, now this is okay, let me redraw this. This is the hemisphere given, okay, and the difference you easily understand, I think. The angle, the flux is entering like this at an angle 45 degrees. Unlike this, this is parallel to the base, the area vector here, but making an angle 45 degrees there. So I can simply write flux in is equal to flux out as well. Inward through the base, outward through the curved surface. The question is flux out through the curved surface. That means if you calculate this, that means you automatically calculated the right one. I can write E dot A is the area of the base. So this is EA cos 45. You can write this is the flux out. Area is nothing but pi A square, cos 45 is 1 by root 2. Therefore the flux out is E pi E A square by root 2. Therefore see the options now. The option 2 is correct one. The option 2 is the correct answer. So now with some more problems and the next concept, let us continue in the next class. Till then, see you. Goodbye.